I'm going to talk to you today about the ARM memory tagging extension, the MTE. It is a feature that was introduced in the ARM instruction set architecture v8.5. So v8 is the 64-bit instruction set architecture, instruction subsetting the instruction set. And it has been revised a few times, and now there's even ARM v9. And the memory tagging extension is available in some devices that have started to hit the market. They are mostly from minor Asian brands, actually. And then there's the Google Pixel 8. It's the flagship device. So let me first talk to you about Christie's handbag. So Christie went on eBay or Tradera, wherever your local thing is, and she bought a Louis Vuitton handbag like this. They are fancy, you know, status and so on. And the leather broke here on the handle. You see, there's like this sensitive part here. There's a tag here. See, it's a tag. And that wasn't all of it. So she takes it back to the store to have it repaired. There's a Louis Vuitton like signature store in most big city cores. And the store looks inside the bag, and there's a tag. And there's actually a tag inside of the bag. Why is there a tag inside of the bag? Yeah, well, it's actually there as a low-key protection feature to make sure that this is an authentic bag. So the store attendants looks inside Christie's bag and they say, it's not one of ours. Like, how could you know? Well, our factories are in Italy and France and a few other places, but not in Moldavia. That's this Tintin country that doesn't exist. Unspecified Balkan, I think. So there's her counterfeit handbag has a signature, like 2-letter code that is for the country that doesn't exist. So the counterfeiters couldn't even get this right, and she bought it off of eBay, and she has been scammed. Well, that's horrible. But the point of the takeaway of this is that this is a low-key security feature. Of course, you can fake the tag. It's not about that, but it requires at least some effort to do so, and that's a little bit what memory tags are about. They provide some kind of security. You can fake them, but they provide a bit of security anyways. The point of this lecture is that you should be able to take away these things. What are memory tags? Second, what is a tag pointer? How is the memory tagging extension using memory tags and the tag pointer to achieve spatial and temporal memory safety within the same executing unit? And as I said, it's the Google Tensor G3 SoC that has this, and it's the MediaTek Dimensity 9300 is the other one that is out on the market that I know about. Vivo, Oppo, and devices like that have this. You may conceptualize about memory in this way. There's a physical address bus, and there's a data bus. This is computer architecture 101, by the way. You should all know this, but let's, just for the sake of the context, let's repeat. There is a data bus here that just transport, typically today, 32 bits at a time, and there's an address bus, and it goes from A2 to A63. So it is a 64-bit bus, but they only pulled not these two last lines, because it's not even byte addressable, it's word addressable, the memory, and everybody's using at least 32-bit granularity. So they didn't even pull these lines. So the two last bits are ignored. By the way, there is no DRAM like this with all of these address bits. It's just a theoretical example. It's too big. It would be like some exabytes. We have a granule, anyways, that it's 32-bit or 4 bytes. And you notice on your pointers in the memory or the physical bus that there's 0 out here all the time. So apparently there are some bits there that are not used. Even if we use the theoretical biggest memory we can have on a 64-bit architecture. 16 exabyte, 2 to the power of 64 bytes. That's a lot of bytes. Yeah, should be enough. Anyways, the point of this is there is something we call the granule, which is like the resolution of the address bus, and in this case it's 4 bytes, so it's 4 times 8 bytes. That's the granule, that's the granularity. And yeah, the connection looks like so, but of course there are some more. There's some write enable, there's some clocking, there's some strobing, some self-refresh, you know. But this is the electronics that you care about as a developer. All right. So memory tags. If you have a memory like that, which just theoretically this just goes on for 16 exabytes, and you add some bytes out here on the side, like here. Let's put in some more bits, like that, on each row. We call that a tag. So there are the 32 bits, okay, fine. And there's some extra ones, there's 9 more bytes here. I took 9 out of spite because it's not 8. just to annoy you guys and girls. So we call this the tag. So this is the data bus here, and then there's something more like a tag bus here. And you physically do this in the memory. You can do that. If you make your own electronics, you can manufacture your own DRAM that has, or SRAM, whatever RAM, that has this property that it has some extra bits like that. And people do. I can easily invent, yeah, so this just goes on for a lot of exabytes or whatever, and every single row here with every granule of 32 bits has an additional tag here of 9 bits. That's the idea here. We can create our own memory core modules, but it has been done in history. Okay, let's take an example here. Instead of adding 9 bits, let's add 24 and use those in groups of 3 to add a Hamming 7.4 code. This is a dreamt up example. It's nothing real. You might use it in some extremely noisy environment. If you went in coding theory or something in university, you would have looked in Hamming codes and looked at Hamming codes, and this is one of those. Because with every 4-bit group, if you add 3 extra bits, you can error correct 1-bit error. So all 32 bits can be error corrected this way for 1-bit error in every 4-bit group. Normally that's not what you want. You probably want to error correct 1-bit error in a 32-bit group, and then it looks more like a SIM module like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 64 megabytes in each of those capsules times 8, and then another one just for parity check. That's how you do it in practice. There's a much better code than what I came up with here. But anyways, if I wanted to make something for space equipment, because the higher up in the stratosphere you get, the more atmospherical interference from space you get, and the more error correcting codes you need in your memory, because it will be disturbed by space stuff. And then you might want to go and do something like this. Something that corrects a bit in 4. So this you can do, and you add, in this case, 1/4 extra of data to every cell on the data bus. And you get, how much extra is it? Yeah, there's a lot of extra bits per byte. 0.7, 3/4, right? Yeah. I could have calculated that if I wasn't so nervous. 0.75 bits per group. So this is group theory or coding theory or whatever you like. It's just like some way to, so just you get the idea that this tagging thing is about dealing with extra bits that you attach to words in the memory. Here's another historical example, is the Symbolics Lisp machine right here, which executes Lisp in hardware. And it has a tagged memory, which is it 36 bits? Yeah. And out of those, for example, you can have a floating point number here of 32 bits, and then it's tagged here in the type that this is a floating point number, and there's a cadder here, or you can have like a pointer or something, And then that has an extended type because you can point a lot of different things, different Lisp constructs, and there's a cadder here. And the cadder is important because this is a stack-oriented architecture, so everything is stored in the memory like lists. And that's basically the foundational idea about Lisp machines. So by joining memory into the architecture and structuring memory with tags in this way, it can execute Lisp efficiently. They didn't survive because they're not super scalar. So they couldn't scale, and the market was too niche and so on, but probably several reasons. But for a while in history, in the 70s, it was a thing you could do. You could create machines like this that had tag memory like that. So it's not entirely new. This is from, I think, early 70s. So yes, 50 years ago. There's a good ACM article about this architecture if you're interested. It was just meant as an illustration. Instead of putting all of the tags out there in a special tag bus, you might not be able to pull out all the lines, for example, from the RAM capsule or the BGA, all of the balls underneath. You can do this trick. You just churn out a bit of the physical memory here, say, you can't use this part of the physical memory because I'm going to put my tags there. Let's say that you see that I want to use like 8 bits here instead of 9 now. So I could group them nicely there. And this way of using some of the other physical memory to store the tags instead of manufacturing special electronics, that's called a carve-out, like with a layman term. Basically because we carve it out of the physical memory that the operating system can use. All right. And in that tag memory that is in here in our carve-out, also called shadow memory in some contexts, we take out 1 byte, for example, in this example, use as a tag for that memory. So we have this 8 bits here for those 32 bits up there. Chill. Then how we access it, that's a matter of the electronics. It's actually the implementer of the SoC that has to figure out how do we access these things. I will show you more later. This layout that I'm showing you here, actually we use in pure software in a memory auditing tool that we call Kazan, the kernel address sanitizer, which is built on the old address sanitizer, which is for user space. And yeah, you don't even have to have the special hardware to do this kind of shadow memory and carve-outs with tags and so on. Works the same way. Yeah, so it goes on like this. You don't have to take 32 bits and tag them. You can tag a granule, which is 4 words in this case, 4 times 32 bits, or 16 bytes if you like. And you can tag them with a tag that's just 4 bits. Same idea. And you can put it in this special memory, or you could put the 4 bytes out there. Some other memory that you have associated with each 16-byte line. And this is what we do. So memory tagging extension, the memory tagging extension for ARM does exactly this. This is hard-coded, by the way. You can't change it. It's 16 bytes, and it's a tag of 4 bits. So it gives you 1/4 bit per byte. 1 bit per 32 bits of tag, which is completely useless for ECC, which was like one of those examples I showed you. But this is not for ECC. This is for memory safety. So we're going to use it differently. All right. To manipulate these tags, ARM has added instructions. Load, store, advance, and generate tags. What it does is, you pass in the address pointer to this address here, and you say, load me the tag for this address. And it will go into the tag memory and get that tag into bits 56 to 59 of the past register. Why bits 56 to 59? I will get to that. And well, the instruction, it's load, store. If you take the top line, load tag, store tag, add advanced one tag, and generate random tag. Then the M instructions, load tag multiple, store tag multiple. It follows the ARM convention that you operate on a multiple of tags. So you pass that as a parameter, how many you want to write or load or store. And the 2 variant, this with a little 2, it works on 2 tags at the same time, which happens to be a byte. So helpful. But you think this over for a while, like that it's in special memory here. Why don't I just like go and write in this memory? Because it's implementation defined, how you do it. You don't have to have it here. You could have some extra, you could do this, what I said in the beginning, like manufacture your own memory with this special tag bus. That's fine. The implementation allows for that. So if you are friends with a memory vendor, Samsung, for example, you can go to them and say, like, yeah, I want let's say 16 gigabyte memory, and every 16-bit granule of that memory should have a 4-bit tag that you put into the silicon. You can do that if you're big enough. So the architecture and the instructions allows for that. And since you access the tags all the time with these instructions, it doesn't matter. The SoC will deal with that, whether they flash it some special strobes and signals on the address bus to write this thing and read this thing, or whether it's just stored somewhere else in memory. So that's why we use the special instructions. If you just want to do it all in software, use Kazan or Asan in user space. So you add these special instructions, and then you modify the kernel, but mostly the C standard library, because people begin using this first in user space. Now you put this instruction. You can run them in any context. All right. Did I have something more on the no? Now we know exactly what tagged memory is and how to manipulate it with certain special instructions. Now we get to tagged pointers. And tagged memory loves tagged pointers. Was that a good? There's a good tag pointer. The idea is something like this. Here's another made-up example. We have a 32-bit pointer on some random 32-bit system, old maybe, Amiga, I don't know. And well, actually, you just use 26 bits to address the physical memory, and your MMU just doesn't happen to just ignore these bits. Usually, they have to be 0 or 1. But if you have a primitive enough MMU, let's say, it will just ignore these things. So you can store whatever you like up here. You just AND and OR with some extra instructions, some bits up there, and they will stick with the pointer. To just say something helpful. Originally, a tagged pointer, like for example in a Lisp machine, must have a type field, must say something like this is the type of the thing that this pointer is pointing to. Is this if you have an object-oriented language, for example, it should be very detailed. So there's the example of the Intel, is it called i920 derivative BII architecture that they made together with Siemens, and that was supposed to just execute ADA programs, and that's a very object-oriented language. So all objects had types, and all of the types were listed in a tag field like that in all pointers, and they also had tagged memory, so they could never reference a memory with the wrong type, with the wrong pointer or something like this. The military committees come up with these kind of things. It wasn't very fast or efficient, but it was good for ADA, I guess. So this is one way to do it. We don't yet have... here's another one. Kevin showed you this last year, right? This is the Cherry pointer, the Cherry or Morello extension. the Morello is the ARM extension, the ARM implementation of the Cherry concept, and it is a prototype, no strings attached. And in general, a Cherry pointer looks like that it has like, here's the usual address bits, actually 63 of them. And then there is some B stuff, and there's some O stuff, and there's some P stuff, and there's a tag at the end, which is 1 bit, whether the tag is valid or not. They use 128-bit pointers, so I just like illustrated it here, like, yeah, that's a very big pointer, but everything on the top 2 lines is just one big tag, in essence. They don't call it tag, but from my point of view, like for this presentation, we can say like all of the top 32 bits, that's just tag. That's an awesome architecture, by the way, but we're not talking about that today. You can see Kevin's lecture on YouTube. It's very good. But what we can do with our current AArch64 architecture, actually I think from the very inception of it, is to use a feature called top byte ignore. So on all ARM 64-bit architectures, you can use the top 8 bits of any pointer to memory for your custom stuff, provided that you activate what we call top byte ignore. Top byte ignore is something that you have to go in and set in coprocessor register, special register in the processor. So that's what we call the architecture in Linux is essentially a big device driver for a CPU or SoC. And there's like the ARM64 directory is a device driver for this kind of CPUs. And it will enable you to activate top byte ignore. If you want to use it in user space, there are some special syscalls and stuff you can issue, and you will get this feature. And then any pointer that you allocate, you can just put whatever you like in the top 8 bits and play around with it. There is blog posts from Linaro by David Spickett, the person at Linaro, who has used this exactly for Lisp interpreters and such things as a toy example. So you can have your type and tag reference in this top byte for, yeah, I don't know for what, for random Lisp interpreter. It's nice, but it's entirely, software implemented Lisp, but you can have the references and so on. I heard somebody told me that the Amiga Basic at one point used some top bits like this, despite it wasn't supposed to tag pointers with the type. So this is, historically speaking, something that people have been doing, and in ARM64, ARM has made it possible to just explicitly ask for this feature and use those top bits for something else. It's available in user space, kernel space, in the hypervisor, and not down there. ARM conceptually refers to these different spaces as exception level 0, 0, exception level 0, 1, and 2. But from my point of view, it's just user space, kernel space, and the hypervisor. So with top byte ignore, you can do a bunch of stuff. There's something called a translation control register, I think is the name of the register inside the processor where you set this up. You set a bit there for each of these exception levels, and you can get ignorance on your top byte. If you actually want to address like 2 exabyte memory, then don't do it. But the thing is, you have to activate it. Otherwise, these top bits will be routed to the MMU, and it will go bananas. So you have to activate it if you want to use it. But as long as you do, it's fine. To operate on these pointers, there are actually some special instructions for that as well. Those sub P, sub PS, and compare P. It's for just comparing the bottom 56 bits. And adding to it or subtracting to it. Not adding, actually. I don't know why adding is not included. I guess you're supposed to do something on the right to increase it. Usually, but you might want to operate just on the address pointer part of such a top byte ignore thing. So if you have this feature, you also have these instructions to use. But actually, those instructions are part of the MTE extensions, which only appeared in ARM v8.5. And by the way, all of the MTE stuff, the instructions included, they are completely optional from an implementer point of view. And with an implementer, I mean somebody making system on chips. Rockchip, MediaTek, Samsung, etc. For them, it is optional. So if you want to make a chip, you can choose to have this. And as I told you, was it Rockchip and Google Tensor that actually implemented it so far? But it's completely optional. It's nobody's mandating that you have to have this feature. But if you do, you have these instructions as well to deal with the tagged pointer, not with the tagged memory. This is for the tagged pointer. But when you generate a random tag like that, it will be stored in bits 56 to 59 of the pointer. It generates something, it's 4 bits, so it's something between 1 and 15. 0 is reserved for unused memory, I think. So you will get a number from 1 to 15, and that will be, which is random, and which you use to tag your pointer with. Why random? Yeah, it's just malloc and free and so on. You just want some tag there. Well, we get to why we want it at all. If you want to read and write them with software, you just do something like that on the right. You just use masking and shifting. Is it crystal clear, or am I being confusing? The top byte ignore feature is used with MTE. So if you use MTE, you by definition also use top byte ignore. So when you activate memory tagging, you activate pointer tagging, and you activate this top byte ignore feature, and then it steals those 4 bits and use them for the tag. So we put 4 bits of tags into every pointer with the memory tagging extension. You have to put them there with software and these special instructions. So what we do is we go in and modify the GNU C library and all other C libraries, hopefully in time. We modify the kernel memory allocator and everything to put in these tags on all allocations. Something random, just whatever, something random, and then write it into the tag memory, the same tag. So it works a bit like that. Whenever I store a tagged pointer into some struct or something, I get like, blah, 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 this 56 bits of address pointer to some address in the virtual memory space, and I get 4 tags, bits of tag up there. It's fine. The void star p is always 64 bits. I will just tag. It will just tag along. You don't have to do anything special other than like put the bits there, and they will stick with your pointer all the time. They will be ignored by the MMU and so on, but they are there. And they have a specific use. The tag is there. I put the tag there as an illustration so you see what I mean. And then, well, let's use this for something. We have a tag that is stored in memory. We have a tag in the pointer. Well, and they should be identical. What do I mean with that? Well, let's activate memory tagging. It's actually not activated all over the place if I turn it on. You get the instructions. OK, you can issue them. You can get bits set into the pointer, bits set into tag memory. Then nothing happens, absolutely nothing, until you do this. So this is the simplified view of the page table on the 64-bit, the large physical address extended AArch64 MMU unit. There's a top translation. Oh, what is this acronym? Top translation table base register, where you put in a physical address of your translation table, and then it moves through different levels, which are just offsets into memory. This one contains an offset into that, and so on. And for every level of the translation table, there are some metadata extra bits. And if you follow this pattern, that in level 1, the level 1 table, you put 0, 1 there in those bits, and 1 and something on that level, then memory tagging will be enabled on that segment of memory. So it's a coarse thing. You turn it on really big chunks of allocation, not on like individual pages or something like that. You put it all over. So for an entire program, for example, which is what you want, an entire memory pool, the heap, for example. If you just want memory tagging all over your heap, well, your heap is going to have an entry in the top level MMU table, and just follow this all the way down. But no individual pages. That's not where you set it. All right. And when we talk about memory safety here, which is what we want to achieve, that is, as I said, protecting a program from itself, an executing unit. It's not about concurrency with different programs, because that's what the MMU is for. It protects different programs from each other. This is to protect the program from itself. You can achieve the same with Kazan in software, or by using a memory safe language like Rust. Somebody's probably going to raise that issue. Yeah, or Haskell. And what MTE actually does, it operates in non-safe languages on this on its virtual memory, and it uses compiler instrumentation in some cases. In some cases, you just instrument heap allocations. Heap allocations are malloc-free, you know, k malloc, k free. This can k realloc, etc. Those are the heap allocations. If the tagged pointer and the tagged memory don't match, this happens. So this is all you need to remember. Like, after understanding this slide, you are free to leave, because then you have understood what the memory tagging extension is all about. Let's say that I have my special, all of my heap, for example, is tagged like this. Every 16-bit granule has a corresponding tag here. Every tag has a unique number, like 1010, and the pointer to that memory, which I use in my struct or whatever, pass it around, it is the same tag. And if those two don't match, we get the segmentation fault. Yeah, it's just an exception. Same type. That's reading into memory you can't access. But of course, you will be told that it was an MTE exception, but it will behave the same way from the program's point of view. Everything explodes. And before some smart person points out that, well, isn't there 1 in a 15 chance that it's right? It is, right? This is statistical attack tool. It's not a. This is not about, you know, constructing a mathematical universe where no problems can happen. That's not what this is about. This is about, like, putting some duct tape out there that will help us. If you want a mathematical universe where mistakes cannot be made, you are free to go and use Sherry and Morello and these kind of things. Yeah, it's fine stuff. We can discuss the price with ARM, not with me. But you can do that. But if you want something that's like, let's make it a bit better, this is a good thing. So all the pointers you pass around when you're using MTE, they have some tag, and all of the memory which you access with that pointer, that memory has a corresponding tag down there, and they need to match. Otherwise, bad stuff will happen to you. So as I said, you can first just put tags on the heap allocations. It's fine. But if you use compiler instrumentation, and this has been added to LLVM, C-Lang, we can also tag stack elements. Well, how does that happen? Yeah, well, you have to, of course, get all stack allocations in granules of 16, otherwise it would not work. So you have to patch the allocator for that, or the compiler, to just use activation records aligned at 16 bytes. It's not such a big problem on 64-bit architectures. And if you're not using user space, if you're using kernel space, we have a special feature called Kazan, which I talked briefly about, which I will illustrate in the coming slides. Here's an example. This is user space. And this is actually verbatim copied from the Rust lecture I had last year. Can be called something like Rust in 40 minutes or something like that. You have a basic block inside of a basic block, and you exit the basic block. So when you assign that pointer to X here, it's pointing to something valid, and you go out of scope, and it's pointing to something that's not valid anymore. And you compile it, and you run it, and it works. because it's a single-threaded application, and the memory is still there, and you haven't done any new allocations or entered any new base blocks. So it works, and it's a very big problem to us that this works, because this is the kind of crap that we are dealing with. Like somebody mentioned a lot of bugs in the kernel, Julia, I think, and they are very often of this type. It works because like I do this and I do this in rapid succession, so it's not a problem. But with memory tagging and compiler instrumentation, what we do is this. Every pointer gets a tag, as I said. Pointer tag in this case is 1110. All right, and the memory it points to up there is also 1110. So the assignment is fine. That's what happens when you do. The allocation is implicit. It happens on the stack. So it's in the activation record here. The activation records is what's on the right side here. If you don't know what an activation record is, you can take compiler course. But when you exit the base block, the runtime of the program has been altered such that it will zero the tags of the activation record when you go out of scope. And the pointer will not access anymore, and you will get segmentation fault because that tag is not equal to that tag. And in this case, it's not 1 out of 16 actually, because I think 0 is reserved for unused memory. Neat. The hardware does this for you. You don't have. You can do it with software, of course, ANDing and ORing and shifting and so on. But neat. So this memory tagging finds a lot of racy bugs, well, scoping bugs like this. So that's how you use it in user space. I didn't show you a heap allocation. You can imagine yourselves like alloc something, it gets a tag, reference it when it's been freed. Same thing happens. Reference something that's tagged with 0. So it's actually a little bit more than 1 in 15. It's a little bit more because you very often the case is that you reference uninitialized memory, which always has tag 0, and you don't have tag 0. So it mostly explodes on you. The probability that it explodes is much higher than 1 in 15. The probability that it doesn't explode on you is much less than 1 in 15 because you're very often referencing uninitialized memory. Right. Everybody's following this. Yeah, okay. Then we have Kazan. So I said that this and all other countermeasures we do with memory safety is about protecting a running program from itself. So if that running program that we want to protect from itself is the kernel, the tool we use is Kazan. In its basic form, what it does is to go in and compile, patch the symbol table of the compiler to override all of these instructions. We already always override these ones because we have optimized versions of memset and memmove and so on for every architecture because you want to write that in assembly. But the top ones are usually intrinsics of the compiler. So the compiler will not just wildly reference and read bytes and bits, etc. from the memory. It will always boil down to these accessors. So we paste them, we patch them in the kernel with our own custom versions that will use a shadow memory with a certain bit pattern here, very similar to the tags I showed you, but I don't put in the details here. It's actually, usually it's 1 byte per 8 bytes, because the slab allocator has a granularity of 8 bytes. Which brings us to the next thing. When you're using memory tagging with hardware Kazan, hardware ASAN, adverse sanitizer, hardware Kazan in the kernel, we set up the granularity of the slab allocator to 16 bytes. Just like that. Because, hey, if it's the tag. You get the tag per the minimum, like the smallest unit you can allocate with a kmalloc, let's say, will become 16 bytes, and that means you can put always a tag on it. It's always aligned as well. So that's the trick, right? So for using hardware tagging in the kernel or MTE in the kernel, the feature is called HAWASAN, hardware ASAN, hardware kernel address sanitizer. And when we use that, we don't need to modify the intrinsics of the kernel as well, because all of the loads and stores that you track with MTE will be the actual hardware loads and stores on the memory bus, right? It will be the MMU that will jump out like an angry dog and bite you in the foot. So the tag will bite you. And that's, of course, much more efficient. Kazan, if we turn it on, the software version of Kazan, that's really hurtful for performance. Because like when you start accessing this thing, you can imagine what happens with the cache. And then it's like for every load and store in memory, you have to go through a loop and read something here, compare. It's a pretty significant performance hit. But with hardware, no problem. You can have it on while you're running. So this is a really good duct tape, I would say. If you have it on your Android phone or something like this, and you turn on memory tagging, the performance impact isn't that bad. It exists, but people don't seem to care so much about that as they care about the memory usage, because, yeah, it turns out that most people don't implement their own memories. Like they have something like this, there's going to be a carve out. They don't have that type of memory with tag. But maybe if this catches on and memory manufacturers get the right requirements, maybe they will start to make memories that have tags in them for every 16-byte granule. That would be nice, I think. And that's it. We are right on time. We even have a few minutes for questions. How can I help you? Did you understand anything? Yeah, good. I should bring up the key slide so that you take this with you. That's the most important one. Eric has a question up there. Okay. Yeah.
Stupid question. This is additional data protection, right? It's not for execution, executable code, additional protection for that.
It's mostly for data. You could have, like there's a type of attack that starts to modify the text segment. Usually you don't memory tag that, I think. I think you map it to untagged.
I was thinking about return-oriented programming and so on.
For that we have a different thing that is called KCFI. Control flow integrity, which I recently implemented for ARM32.
I like to learn a little bit more about that.
You want to hear more about KCFI?
Yes.
All right. Yeah, so KCFI works this way. For every function entry in the program, including the kernel, you instrument LLVM or CLang to insert a signature of the called function. I don't know exactly the algorithm, but it has something to do with the arguments and so on. Like if you pass in an int, a pointer, whatever it is, you pass in and you hash this and you put it in 4 bytes right before the function entry in memory. And when you want to jump to a function, the runtime will be patched to read the 4 bytes prior to the first instruction of the function you call in memory and compare the signature with the expected one from the callee. So if somebody is trying to disturb the control flow and get it like to return from some other place, they are in serious trouble at that point. Call, and then there's guarded control stack, and that's for the return-oriented programming protection. And I don't know very much about that. I just know that it exists.
Yeah. So I learned quite a few years ago about return-oriented programming, where you find little sequences of code. And I made the connection with Forth and other languages. And recently, Forth implementations only need 9 primitives, 9 little places in your whole memory that does things. And then you can bootstrap from that.
Oh, nasty.
Yeah, that's the latest. So if you look at Forth and other languages, you learn about how few primitive operators you need to do this kind of attack.
Yeah, and that kind of thinking is probably very good to have in the back of your mind if you want to do this kind of attack.
Yeah.
So the countermeasures we have put in hardware for this kind of return-oriented programming, like it's mostly the guarded control stack, I would say.
Yep.
And then there is a CFI is for forward jumps and guarded control stack. If I understand correctly, excuse me if I'm not read up on these details, but that's for return-oriented programming. So next year I will have a lecture about the guarded control stack, and we will talk about that.
Thank you.
Pardon? He says yes. I trust him. Yeah. Yeah.
Yeah, so it is the same as Shadow Stack that Intel
Shadow Stack, yeah.
Intel processor has.
Yeah, we can't use they ARM, which I happen to work for sometimes. They cannot use the same name for trademark reasons.
Exactly, yeah.
But guarded control stack, which is the academic name for what you want to do, that is supposed to protect better. And then we have the other one, the early patches we made, the first things, they are the come from instruction. I don't remember exactly what it's called, but it's a branch target indication, that's what it's called. So you can put like a binary offset that you're allowed to return from, so you can't like return from anywhere. But that can be circumvented, so it's not as good as the guarded control stack. But now I don't know how the guarded control stack works, so I have to go and read up on that, sorry.
Maybe I can ask. Yeah. So the main effort for this tag pointer to work is that you have to patch libc, probably malloc, and the memory allocator. But what about the other memory allocators which are out there, like jmalloc, the others which tend to do a better job?
Yeah, the patches here have been done to glibc and to the kernel malloc allocator, and then, as I said, to the compiler for all of the stack allocations. Then you have to go and patch every one of them to use it, yeah. Right. For BPF, for example, but that should be safe by itself, so why? But you should probably want to patch that allocator as well, and whatever allocator you have that could use it and can contain something that you can exploit. So if it can only contain like, I mean, it's not a DRM tool. If it's just secure buffers for some Netflix stream, I don't see why you would want to tag that. But if it's an allocation that has to do with your that can be attacked, then yeah, then you need to add it manually, or somebody has to add it for you manually.
Okay, thank you.
Joachim had a question.
Yeah, so if you allocate more than 16 byte, which happens from time to time, do you tag all that memory, only the first 16 byte?
Yeah, when you allocate, if you say malloc and push in, I want a megabyte, the allocator will loop over all of the tags and tag them with the same tag.
So if you take your fine example with the X, Y, C code there, so when you, on another slide, so when you end that one, yeah, so when you end, no, well, maybe when you...
That's stack allocations, so...
Yeah, but yeah, you could exchange it for malloc and free or whatever example. So when you malloc, you need to actually iterate that entire megabyte and tag it.
Yeah, that's why... Oh, good question.
And
best
also this particular example, I would like to see the assembly route, but I guess you need instructions when you enter or leave the context there.
Yeah, there's the multiple instruction there, and that's... First, you have this for 2 nibble granules, so you tag 1 byte at a time, and that can so you can tag like 32 bytes at a time. But then you have this many, which is just like I say, I could tag a megabyte with this tag.
Okay.
So that's fine, and then the hardware will go and write the tags all over here.
Usually, the M in ARM instruction is to just use multiple registers. But yeah.
Not in this case. Or is it, no, it's not multiple registers in this case, no.
And yeah, while on this slide, what's the G for?
Tag. Yeah. I didn't name these instructions, I'm sorry. there you.
How is the tags shared between processes?
Yeah, you have to deal with that. Well, the easiest way is to not tag shared memory. Sorry. You have to deal with it. That's the short answer. It's up to software to deal with it. Or you have to pass the pointer in the tagged fashion. Like, for example, if you pass it with one of those, what is it called, this IPC that's part of glib and so on, dbus. If you pass a pointer over dbus, you pass the pointer. So it's going to be, in there, that pointer is going to be like the same. So problem solved. But there are probably elaborate mistakes that can happen, I'm pretty sure. Are we done? One more. Oh yeah.
Yeah, I'm not sure if you said, but what is the runtime overhead of this? Like the extra stores and loads?
Yeah, but that's hard to say. That depends on how the implementer has implemented their tag memory. So I haven't done any benchmarks on anything, but okay. On the Google Pixel, it's apparently negligible.
Okay. I was just thinking there's going to be more instructions in your instruction stream, no matter what.
Yeah. Performance is, I think, not a big issue with this. Since it's all with hardware. I mean, it's something of an issue, and I think people have been looking into how do you cache this optimally, and these kind of things you can easily think about. But that's for the computer architects. But there's so much things that the implementer has to do, which is not done by ARM. Let's say they just implement the instructions. So like how fast the memory is, how do you strobe it, do you have special tag bits, do you not, do you have shadow memory, how is that bus oriented, how wide is the bus, all of these kind of things. So you would have to benchmark a real system. Well, maybe somebody out there has numbers on the Pixel, for example, or the Oppo, one of those.
Yeah, I think it necessarily is very dependent on your architecture and how you designed your system.
I have a backup slide. What people usually ask is how much memory it takes if you have a carve out. And that's exactly the 3%, 3.125%. So do you think it's worth these extra bits to have this security done engineered? I mean, it's not for all of your memory, it's just for those that you use for allocations. So of an important kind.
Just write in Rust?
Yeah.
No.
You can do that. That's a solution. But this is for things that are not memory safe. Or anything in Rust that is tagged unsafe. But you wouldn't ever write anything like that, would you?
Right. I think we've already stolen so much time from Jürgen, who's the next speaker. But we can continue in the break afterwards. So.